So good morning. Thank you, Fred, and thank you, Carl, for inviting me. It's my great pleasure to be here. I've heard so much about this conference, and I've never actually been to one. So I'm very glad to see. I don't know if you start like this every time, but it's a very nice beginning to a conference. You know, when Dvořák was in his middle ages, he moved to America. And I was thinking, it takes a lot of courage to move to a new place. When you are in your existing place and things are already working and things are fine, and you go to the new place and you're not sure how it's going to be, and you're not sure if it's going to work out, and your ideas are not clear. I think today, in language processing, we are in very much the same position. I was surprised, quite surprised to hear that at the last conference, when Ken Church gave the invited speech, he said roughly the same thing. He said, we are, as of about 15 years ago, very solidly rooted in an empirical paradigm, a paradigm of experiments with measurements, with evaluations, where you have to produce recall and precision measures when you're finished, otherwise your paper is not complete, etc., etc. Now, those of you who are older than, 40, probably remember the days before 1991, before the change that was introduced by, for instance, Fred and other people. Yes, it's okay. This is my opening. So those of you who are older than 40 and were around before 1991 will remember that there was a very different paradigm before. Now, you can say, what is wrong with today's paradigm? Why is there a feeling among many people, and I heard this again at the Coling ACL conference in Sydney in July, why is there a feeling among many people that our field is getting sterile? Now, many people will disagree. Your conference here, I looked at the proceedings, is a very good example of why you say this field is not sterile. It is doing really interesting work. It is doing very scientific, empirical, well-defined, good methodology type research. And yet, there are many problems for which the solutions do not get better. Information retrieval has been stuck at about 80% recall precision, or even less. Information extraction has been stuck around 80%. It's getting slightly better. Machine translation is getting slightly better, but if you look at the places where it is getting better, it's either getting better in sort of just having more data to play with, like Frans Och at Google, or it's getting better by slowly recreating in the empirical paradigm that which was known a long time ago with syntax-based parsing and so on, my colleagues Kevin Knight and Daniel Marcoux at ISI. So you might say, and some people believe, that there is an upper limit to how far you can go with today's empirical-based experimental sort of paradigm. What I have to do today is to give you an argument for the future. I believe Ken Church ended his talk last time saying, what is the future? And he didn't know where to go. I would like to describe to you some experiments we've been doing at the request of DARPA to try to point toward one future to see, is it possible? Is this a place for us to go? Or is this not a place for us to go? Now, it is frustrating for me to give this talk for two reasons. One is, it is not your paradigm, and I don't think you will find the talk satisfying because it doesn't fit into your current mode of thinking. And two is, the work isn't finished. We do not have the time to finish because I don't know if you know DARPA, but they are impatient. They are the funders, and a lot of their decisions control what happens in the whole world 5 years later to 10 years later. When they put money into something, many people do that something, and that something becomes the paradigm. As Fred and others will tell you, that's what happened in 1991 when they started funding the machine translation effort that had been doing statistics-based machine translation since 1986. Okay? So this is the experiment I would like to describe to you here. The experiment called learning by reading. And I will go very quickly through it, and because it involves some knowledge representation work, which used to be part in one bag with natural language processing work in the 60s and early 70s, and then split, and has never come back yet again, some people believe that is because that is the reason for the inadequacy of our current systems. They cannot understand, they cannot reason, all they can do is simple transformations on the text, adding information in or transforming some things. They cannot go beyond this. To go beyond, you need more techniques. This is an experiment or a set of experiments to look at one possible simple way in very short time to put these techniques together, just to see what do you get. Let me describe to you now. I'll start the argument from McCarthy, from the AI point of view, and I'll go through what we did. And at the end, you must pretend you are DARPA. You must listen to my story, and at the end we will vote, and you will tell me, should we try this as the new paradigm? Should we continue with the old paradigm? Should we try something else? Okay? So please, if you don't understand all the details, and a lot of it is unfinished, too bad, okay? But think of the bigger picture. This is what John McCarthy, the famous AI person from Stanford, says. In a sense, the field of AI is still very young because the challenge is so great. A key thing that has not been achieved is to be able to learn about a subject from text, says McCarthy. There is an enormous amount of information on the internet, but AI has not advanced to the extent where this information can be effectively used. I think that is not completely true, but that is mostly true. No computer program today can really use Google. I think that is almost 95% true. Yes, you can sort of pull some information in, but the human has to do all the work. To McCarthy, it is just a question of time. Now, what is the problem? Why is it that no computer program can actually use this information on the web, the text, not the pictures? Let's leave the pictures, right? Well, you need semantic understanding. You need, what does it mean to use? You need to bring this in and do something with it that is not just adding little things, little small notations inside the text. You must actually do something and produce something or act some way. You need, therefore, wide coverage lexical semantics. Lexical semantics at a deeper level than just the word, the kind of work that James Pustiowski will tell you about his work, for instance, in 2 days' time. You need deeper representation so you can support some kind of reasoning so you can do something. And what kinds of reasoning? What kinds of actions do you need to do? You need to do probably word sense disambiguation, co-reference, anaphora, quantification, negation, all the standard problems that computational linguists, and even philosophers have worked with, sometimes for several hundred years. They have not been solved, and you can show small case by small case that you need them. The question is, do you need them all to be solved? And how deep must the solution be before your system can do something real? What is it that you can take from today's new paradigms and from the older work and put together? Can you get a new fusion that you can say, okay, here we must try something new? Okay? Evaluation is the big question that we never used to do in this field, that we now always do in this field, and it is completely unclear how to measure. So this is something that when we vote, you will probably come back. I will come back to this at the end of the talk, almost half the talk on this question. And you must tell me if you believe it or not. Now, why are we silly enough to think we can do something now? Why? Well, we now have robust parsers like Minipar and Charniak parser and Collins parser and Context and various other parsers. These are trained statistically. And they can take a text and produce something that is not a simple text. It's a two-dimensional tree-like structure. And maybe that is useful for some things. Okay, for machine translation, it looks as if it's beginning to be useful to get higher scores in simple phrase and 5-gram phrase length things. We have large, shallow, semantic, quote-unquote, resources like WordNet and other things, which may be useful. We have progress on knowledge representation and reasoning systems. There is progress in the last 20 years or so. They are bigger, they are more robust. They don't have to do full, complete, logically sound inference. They can work on subsets and do some things like Psych or PowerLoom. There has been a project called HALO, funded by a colleague of Bill Gates in Seattle. It was funded for 1 year, in which people took one chapter from a chemistry book. By hand, they made the representation. They took questions from a high school book. They made the representation of the questions. They put those questions in the systems, and the systems, all 3 systems, passed the high school chemistry test. They did not do very well, but they did pass the test. The problem was that the knowledge had to be brought in by hand. If you can take a computational language system today, a text-based system, and take the knowledge and bring it from a high school textbook into the machine by machine, and then you can do the reasoning by machine, can you pass the high school test? If you can pass the high school test, which you will agree no system can do today, will you think that is an interesting advance in our field? I would say that's an interesting advance in our field. I would say that is something completely new. That is a paradigm shift, because it involves new techniques, it involves the best of the old techniques, it has an evaluation in, everything is cool. Can we do this? That is the question of this talk. Now, we know we will fail. We know we will fail, right? The question is, how will we fail? And if we fail, do we fail in a way which promises that there is an answer in the future, or do we fail so badly that there is no hope and we must do something else? So you will vote at the end of the talk what you think. Here is the architecture now for a system that DARPA has funded for 1 year, almost 1 year and 1 month by now. It's called Mobius. There are 2 parts to do this learning by reading. The right-hand side loop is, here comes some knowledge in. You have, in step 2, some kind of parsing engine or something like this that reads the text. It looks at the corpus. It integrates what it pulls out of the text into some growing knowledge structures or knowledge base or something that goes into this middle thing there. Then the system looks at what it knows and reasons about and adds and runs inferences and comes around and adds to this middle thing. And you have like 2 cycles, like a Mobius loop, going round and round. DARPA funded about 5 groups to work on this for 1 year. Small groups, pilot study, just for 9 months and then a little bit of extra, which we are now coming to the end. And they had a whole group of about 25 AI specialists from all around the world, and we met every month or every 2 months to talk about the different pieces. The main groups looked at these different areas. The first group was Northwestern University, and they focused on reasoning of an introspection, they called it, on the knowledge. They took a small set of knowledge, a few sentences, and they built all kinds of reasoning rules, and they showed how the reasoning can grow more knowledge, etc. The next group of people was Psych. This is a famous company that builds large-scale ontologies in Texas, and they have all kinds of big stories about the reasoning they do and all kinds of axioms and an ontology with over 1 million axioms and all kinds of things like this. They looked mostly at the knowledge repository, and they looked at how you can use axioms and inference to build knowledge around places where you don't have knowledge. So you have knowledge about something, a new text comes in, there is a new word you don't know, you find the hole in your knowledge, you say this word must mean this hole, you see what you can do there to learn. The next group, and the nicest work I think, was from Boeing. Boeing, they have a research group. You didn't know the people who make airplanes. They have a research group, and they look at integrating knowledge. They take text knowledge, which they code by hand. They take existing knowledge, which they code by hand. They put them in, and they see how they can integrate. The final group was us, and we look at what you can do with automatic modern techniques on text, what you can do with parsing, with converting to knowledge, and how can you push this through. I will describe a little bit this, and then I will describe what happened to this group and how it's going further. So here's the talk. I'll describe first the project. I'll describe the pipeline of reading and learning. Then I'll talk about evaluation, you'll see. Then I'll talk about the modern Mobius project, which we meet every month. We're meeting at ISI next month, and I'll show you what we are doing there, and then the conclusion, and then we vote. If you build a Mobius system, now think for 1 second. If you must build a system like this, and I give you 9 months, and I give you $300,000, what do you do? What do you do? I tell you what we do. We say, first, we just say we get the words. Just let's say we take the chemistry textbook, the high school chemistry textbook. Let's just look at all the words there. We sort all the words. We put them in the different parts of speech classes. We find out the frequency. We find which ones are important, which ones are unimportant and stuff. We put them into some kind of structure. We say, these words, we don't know what they mean. We take them as defined. We cannot spend all our time to learn these words because we do not start at the age of 1. We start at the age of high school. So we take our existing big knowledge structure with all its knowledge called omega, the ontology. We take the words here, we put them in, we create a small one just as background knowledge. Then we look at the relations between words, and here we use modern techniques, statistical learning techniques, and I show you how we do that, to find out how words start going together. Then we take some text, and now we start the real learning cycle. We run a parser on the text. We bring the information out of the text in some form. We put this into some knowledge form, some representation, some propositional form that later we can do inference. The question is, what form? How do we make this? You have to design this stuff. I will show you examples. You put this into proposition networks, and then you put this, you have the whole thing ready to go. Now, maybe there's pieces you don't know about. So what you would like to have is a small information retrieval engine to go look at the text, to say, here is a word I don't know. Find me other places in the book where we talk about this word. Find me its definition, examples, further descriptions. Let me parse them. Maybe I can help myself. Maybe that will teach me what this word is that I don't know. So you need a small information retrieval cycle in there, which we call targeted reading. Okay? Then you start saying, now I've got all this information here, and I put this into the proposition networks, and I can say, well, okay, I know this piece. I can just add this to the knowledge. I don't know this piece. I do the targeted reading. I start making this double loop. You can see the place at the bottom where it splits. Here I go more targeted reading. Here I go back to the knowledge pool, and I grow things. And now we do the test. In come some questions. I read them. I find the targets, the places that I must find the answers. I go bring the knowledge graphs there. I bring the knowledge and I say, here's the question I want to know. Here's the piece where I must do the reasoning. I find similar graphs. I go match up here. I find the answers. We do not try to do formula reasoning or graphic reasoning, so that is out, okay? But everything else where you can do sort of standard inference, we try to put in here to see, can you make it work? What happens? What does it look like? Now we have 3 months. Right? 3 times 3 months. The first 3 months is the green zone, and we built all this in 3 months. We just take very simple existing solutions, we put them together. The next 3 months is this orange zone there, and that is to put together the reasoning, the conversion into propositions. And the last 3 months is the question zone. And that part, when we started it, they changed the whole problem on us, and they put us into a new project, which I will describe to you in a second, to try to make a demonstration system. So we are here, we have built this system except for the last part of this purple zone, but I will show you what we built instead. And so I'll show you the whole story now. Here's the text. It's a high school chemistry textbook. There's the text, there's the information. It has about 313,000 word tokens, 12,700 different words. When you do some kind of word analysis there, you find, for instance, that you have 12,700 types of words, of which about 146,000 different nouns, 9,000 different nouns there. If you look at the different nouns, you say if you learn the first 200 nouns, you represent them, you have covered 96% of the corpus. If you learn the first or represent the first 50 verbs, the most popular, you get 92% of the corpus, etc. So you have some sense that it's not an infinite amount of work if you want to begin by hand before you can cover the basic knowledge in there. Of course, many words come in groups like this, like practice, exercise, solution, analyze, equilibrium, constant, etc. So you go find them, and you find with mutual information which are the most common ones of these. You put them out, and you put them into this table. And we do all this work up front, and we build our little background library or knowledge base of terms that we are not going to try to define. Then we can go read those terms that are defined in the book, new terms, take them away from this and go read them and see, can we learn their meaning from what is said in the text using these predefined, supposedly known other terms? And can we then reason with them and answer questions? Okay? So we must build a starter ontology, this background knowledge. We use our ontology called Omega. We build a small version of it. We get the coverage of about 6,000 of these already there. We add another few thousand terms in there. So we have that. We take a knowledge information retrieval engine. We build a thing called Scout. It's a version of Lucene, which you can get from the web. And we have it there. And this we run on the book. So this is on, it's all there. So this is all the background knowledge. We do this. This is part of what we do in the first 3 months. Now we get to the interesting part. What does it take? What must you do to learn and to read? So we build this following pipeline. In comes some text. If you read a sentence, and it looks just like a normal sentence and it tells you some stuff, you learn it as an axiom. It says, all acids have the following qualities, all acids taste this way, acids are the opposite of bases, etc. like this. You learn these, you put them, you represent them as axioms, you put them in the knowledge base so that it can use them for inference. Well, you also use statistical methods to find relations between terms, and I'll show you how we do that using mutual information there. Then you produce for everything some logical form. And this is the part where you, being not being knowledge representation people, probably have no background knowledge and don't care. But that is because you are younger than 40 years old. If you're older than 40 years old, you know that in the old days, you used to care what is the logical form of what you produce. You didn't just do little decorations on text and add little extra terms inside text and so forth. That is actually an important part, or it could be an important part of your future. That's why you should care. I will show you some examples. You get then definitions, axioms, and so on. You put them in there or in the knowledge base, and then you're ready to do some reasoning. So this is the sort of reading part. Okay, step 1, parsing. Now, you have a big problem. There are thousands of knowledge representations out there. Which one is reasonable to use? Which one is simple enough to make sense? We used, of course, the one of our own colleague, Jerry Hobbs, because he's one of the most respected and famous people in the field. He has a book, or he's working on a book called Discourse and Inference, which describes a simple but usable knowledge representation scheme that is sort of based on first-order axiomatization of English. And it's something that is easy enough to convert from text automatically. I'll show you examples that you can do something with. It is based on his approach of what he calls ontological promiscuity. He says, don't make a few small primitives where you try to define everything compositionally. Make many, many primitives, 100,000 primitives, and just use them, and then try to learn how they connect to one another automatically. That's a much better way to go. That's a fundamental decision you have to make, and he makes it that way, and I think he's right, actually. So, in comes a sentence or a text. You tokenize, you parse. So we try with different parsers, Minipar, Charnek's parser, Hermiakov's parser, and so forth. And for the beginning, for this book, we took every sentence in the book, we tokenized everything, we parsed every sentence in the book, and we put them in there. Now we must say, is this correct or not? What does it mean to be correct? How serious is it if you make a mistake? To go from the parse tree, you have to go into a logical form. You cannot do one jump, because there's too many steps in between. So we took some technology we have from statistical machine text summarization called basic elements, where you take a parse tree and you break them into small little pieces, the pieces of the parse tree, and you create small triples where you have a head and its modifier and the relation between them. We use this in summarization to evaluate summaries. If you give me a text and you give me a summary, and I can take the small elemental pieces, then I can look how many of the pieces in the summary are present in the text. And when you give me multiple texts on the same topic, I can see which pieces overlap at the elemental level, and I can find out what is the content, what's the information overlap, the content overlap between my summary and all the texts you give me. Okay? So we use this to just go and take the parse tree and produce small little units called basic elements. I'll show you in a second more. From these small elements, we have a toolkit called the logical form toolkit to convert this into simple propositions. So here's an example of the output. At the top, the atomic theory of matter sentence. Here we have just the normal parse, and then we produce the basic elements there. In the second thing, you see the atomic and matter and the theory at the top there with linked. Here we have then some intermediate form with all kinds of other information that's unimportant. And at the bottom we have here we call shallow logical form, or Hobbes' normal form. We call it after Jerry. He doesn't like the name, but that's the name we use. And there, for each word, there is a small proposition, and for some other things, there are extra little propositions put in to capture some information about determiners and about plurals and so on. I'll show you in a second how. This is how you go from a simple English text to a simple parse tree to something slightly deeper. But first, what is the parsing statistics? We run the Charnek parser. There are 12,000 sentences. There are 51% of them have an error in. Okay? This is the reality when you run the Charnek parser on something that is not newspaper text. So there are about 7,800 sentences. The average number of errors per sentence is 0.6, and here are the kinds of errors you get. It took about 40 minutes to parse the whole book. And then to create these little triples took about another 6 hours or so. And then to create the logical forms took another 15 minutes. So you get a sense of how the breakup is and where the work lies in there. Here's the Hobbes normal form. This is this intermediate form. I just want to show you 2 or 3 things. You take a sentence or you take a phrase, a black box. For each word, the theory is there is some meaning to the word, so it must be reflected somewhere in here. But words like A don't have very much meaning, so maybe we can drop them, or maybe we need an extra theory for what A means, and they introduce some other stuff. But for words like black and box, they introduce into the reasoning system some content, right? They introduce in Hobbes' theory 2 kinds of content. The fact of blackness and the eventuality that blackness is what we are talking about. Because these are two different things that you need to be able to reason about. You can talk about blackness in its truth, or its not true, or its potentiality, and so on. So here is the potentiality, the eventuality, he calls it, and here is blackness, qua blackness itself. Here is boxness, qua boxness, and here is the eventuality of boxness. Is it true? Is it hypothetical? And you can put them together. Now you will admit this is extremely crude and extremely simple. Yes, that's the only way it can work. But it is enough to allow you to do some interesting inference. To do this stuff, Jerry has been building a toolkit, and it is more or less complete. It can produce about 60% of WordNet's definitions. It has parsed 100% of WordNet's definitions. About 60% of them it can produce completely correctly into this logical form here. You can download this thing here, and it has rules which you can build yourself that looks like this. Here's a verb called composed of, and that gives you this kind of form, to compose with the predicate, the argument structure there. Here's the auxiliary is. It goes to some primitive be with two pieces and some present tense here. Here's atoms, which is a plural. So there's the atom, its eventuality, its truth, and the fact that it's a plural, introducing a set variable. So you can talk about the atom or the set of atoms, whether you talk about X or S. And X is this thing, and its truth or eventuality is that E. And the set you can do other things with. You can group the set and so on. So you see how you decompose step by step the phenomena. Plural goes one place, determiners go one place, because these things are things you need to reason about. And the primitives that you don't really understand what they are, you just leave them as these symbols more. And you make a little prime like the semanticists do, which I think is a trick, obviously, but it's a clever trick because it allows you to proceed. I used to think it is a stupid trick because it doesn't get to true meaning. Now I think it's a clever trick because you can do something and you don't really know the deep semantics of these words. Now, I see by your faces, you look at this stuff and you say, what is this garbage? You are used to working with text at the shallow level, right? With English, with statistics. You group them and you do all kinds of statistics. You say, what is this nonsense? I'm sorry, but this is the talk. So just listen to this talk and swallow your disgust. And then at the end we can vote.
What was the layman's view of what that captures? Otherwise it's quite hard to read.
This stuff here? What this tries to capture, and which you must swallow your disgust, is some kind of representation of the meaning of these words. But not the full meaning, just the beginnings of the meaning of these words. You don't think about meaning when you do modern-day computational linguistics. In fact, you stay away from this meaning. You work at the word level where you look at combinations of words. And if somebody asks you, what's the meaning of this? You say, meaning? Who cares about meaning? That is a very strange answer for somebody who purports to work about language. How can you work about language if you don't talk about meaning? I ask you, right? That's where this view of the sterility of our field is coming in. We ignore the important part of the field. We just look at what we can do with counting words and grouping them together in clever ways. This is trying to go one level deeper, and so you have to invent a new language, abstract sets of terms. And this is the simplest possible thing you can do to try to get there. Okay? You do not believe me, I can see by your faces, but give me another 20 minutes, okay? Yes?
Just very quickly, read out. You see, for example, for the verb composed of.
Yes.
Could you read out in English what the line underneath it says?
Okay, thank you. I should do this more. I'm under time pressure, so I cannot go as much detail as I want. It says that there's a verb, in English it's called composed of. What does this mean in logicese, in HNF, Hobbes' normal form? It says there is some primitive called compose with a prime. We don't know what that thing is, okay? Because we don't have 25 years to develop a whole theory of composition and stuff. But we do know that there is an eventuality that compose could or could not or may or possibly exist and so on. So we need a little variable there that will take a value later on that will say, is this a real composing that's happened or a potential composing or a composing that happened and so on. So all the eventuality, all those kinds of information sit around that E. Then you see arg0, arg1, and arg2. That is, compose takes three pieces. It takes the stuff that you are composing, the joint thing, and you take two pieces at minimum that you join into this arg0. So arg0 is, compose takes three pieces. The first one is who does the composing, that's the agent of the composing. The next thing is what are the pieces that are being put together, and the final thing is what is the result. This comes from the prop bank that is being built by Martha Palmer. So for all the verbs, or about 6,000 or so verbs that she has, these is the frame structure, the structure of, for each verb, how many pieces does it have, and for many nouns, how many pieces does it have. The people, the FrameNet people at Berkeley, they do the same sort of work. Adam Myers at NYU is doing the nom bank. He's doing this for some nouns, like explosion, also has pieces, like what is it that explode, who made the explosion happen, and so forth. So you need this to be able to join pieces together. When you have something, a sentence about the compose of, you will have here some other pieces looking like this, and they will join together. So something will fill arg0 and something will fill arg1. Those are variables. And so you can create a small network where you have compose of, and arg0 is some other thing, and arg1 is some other thing, a chemicals, and arg2, the result is some other thing. And these are arg0, arg1, arg2 labels. In here you have more little primitives with more labels, so you construct this larger and larger network in an abstract language. This stuff you give to the knowledge representation system. This is very simple, standard knowledge representation technique. The knowledge representation system has rules that looks at the forms of these networks and says, if you give me a network of this form with these pieces, I can produce more. And if you give me that, I can produce more. And so it can grow and explode its knowledge. When you give me a network with a structure with a hole in the middle, and you say, this red one I want to know, I can match that hole, and I can try to find where I fit. And when I find what that hole should be, I tell you that's the answer of the hole. I will show you some examples. That's essentially the way the reasoning process goes in these logic form type reasoning systems. The art is to take a flat English sentence, to convert it through rules like this into little graphs, and then to throw this all into one big knowledge system that puts them all together in large graphs. Okay, let's now go to step 2 here. This is very much what I said before. You start with a text, you take all the important pieces. So in fact, since if you cannot read the whole book, maybe you can take a book from some students where they make the yellow lines on the important pieces. You just read the yellow lines there, right? You parse this. You convert to the flat form where you have all these little statements there. Then you go and introduce, for each important phenomenon, like plurals, you must have a set. So you can talk about the elements and the sets. Like when you have you want to know it's for all. This holds for all things because your reasoning system needs to know to apply this rule to everything. If you see there is one, then you want to know the other quantifier, not for all, but there exists one, where you want to introduce one particular element, but not apply this for everyone, and so on. All the things you learned in logic, if you learn some logic, you put these in, and eventually you get to what's called horn clauses, where are simple little triples that try to represent elementally each little piece of the sentence and the relationships between them, either as a graph or a list of propositions. And then you use this as theorem proving. Okay, so here's an example. If we have all atoms of a given element are identical, we get to a little sentence up there. So here we have all in English, just there. And there we have the set variable, because it's a set, many things. And there's the eventuality. Are we talking it's true or maybe true? Here is atom. We don't know what an atom is, but we create this symbol for it, atom, and its eventuality E1, and its symbol X. And atom is plural, right? So there's the S of the plural. That's the set, again, the same set as here. And there's the X, the same atom as atom. Of, we don't know. It just links some things. It links X and Y. What is Y? It's this given element. There it is. And there's the identity. And the main assertion of this saying, okay, this E4, this identity, this fact that they're identical, that's the main assertion. That's the entry point. That's a technical introduction we need there. You then convert this using some rules into this horn clause form where you put the for all inside, because that's what all means. It means for everyone that you ever see. You put things like this. And at the bottom, eventually by rewriting, you get something like for all. That's what it means. If there's an atom and another atom, then there's an element here, and this is an atom of an element and an atom of an element, then they're identical. Okay, I don't have time to go into this in more detail. You can read Hobbes's book, right? All I have to show you is it is possible through a series of small elemental steps with an appropriately shallow representation to do this transformation. Then I have to show you that with this transformation you can actually answer questions. If I can show you those two things, then you can say, well, maybe we are ready today to take a textbook, put it in this form, put it in a reasoning system, take questions, put it in this form, put it in the reasoning system, and get answers. In that case, we can say maybe we are able to do reasoning, learning from text, things that we cannot do today. But, and I hope here you do wake up. If you look at this, you can say, well, you know, with my techniques of learning and my shallow transformational techniques that we do today in computational linguistics, I can learn this, and I can learn that, and I can learn that. And if somebody gives you a corpus of enough stuff, you'll just learn it. So DARPA says, well, if somebody can make the roadmap where we must go and what things we must do, then we can bring the power of all these guys who do the statistical learning in language processing and speech processing, and we just use them to do this. And we can bring the power of all the guys who do knowledge representation work, and we throw these things into the knowledge representation systems, and we see what happens. And then maybe we can have a system that can read a manual of a tank and can answer questions, or a manual of an aircraft and can answer questions, or a manual of how to use your television or your VCR or your cell phone and can answer questions, or that can read a high school book of chemistry or of biology, of history, and can answer questions. That will be a useful future, yes? So DARPA is interested in this, which is why they fund it. Now, to convert, the final step of conversion, I don't know if I have time to show you this, but we use a little, an inference, an engine called Minitacitus that does what's called abduction. It's a way of reasoning out of all these different formulas and finding the best combination of them. And so for a small sentence, for instance, I can show you here is a set of possible interpretations with, as you see, there's each, and there's a plural, and there's another plural with the two set variables. And here are then ways in which you can, these are the rest of the sentence, the propositions. But these expandable propositions in this column are ones for which I have a rule. Each has a rule to expand it into logic form. And so I can apply these rules. And this, what we do is apply these rules in different orders to get different possible interpretations. Okay, I don't need to show you much there, but it shows you that there's a way of combining. Here are about 10, 12, 15 interpretations of the one little sentence. Here's the one interpretation. There's another one. There's another one. That is the sort of most, according to the system's internal cost rules, the best interpretations. There are other interpretations that are not so good. There's one that's really bad, and so forth, according to all these technical reasons. All right. So this is stuff that you can do if you want to play around with the logics, and if you go more toward logic side. Okay. And eventually you get these kinds of forms which look like logic, and the question is, how much work does it take to produce this? Is this a bottleneck or not? And the answer is yes, it's a bottleneck. So that needs some kind of people to work the little theories. What does plural mean? What does every mean? What does the mean? What does quantifiers mean? What does negation mean? What do these different operator words mean? And for each of them to write a set of rules for what logic to introduce, and then to produce a corpus, and then the machine learning people can come and just learn. Okay, that's the short end of that story. Now, here's something that you will like more. Okay, so now you can relax and say, finally I can understand a bit. Here is something about learning relations between different words. If I give you two words and I want to find what's the relation between them, or if I give you a relation and I want to say what's the answer of the relation, how can I find this? One of my students, this he did for his PhD thesis. He's now working at Google. He makes more money than I do. He's 29 years old. He built a system to produce the patterns by which you can then learn relations like birth date. And he did it through a very simple way. If I want to learn birth date, and I want to give the system Mozart, when was he born, and Beethoven and Dvorak, when were they born, then I can give to AltaVista or Google the pair Mozart and 1756, yes? And I can get 1,000 sentences or 10,000 sentences. And I can do pattern matching on those sentences, and I can find that a good way in English to say birth date is Mozart, open parenthesis, 1756 hyphen. That's a way in which English says birth date. Yes? And many other languages. And then here's the death date, and so forth. So this system automatically produced things like this, and then produced little regular expressions out of this, filled with parts of speech and other variables at the right time, and you get name, birth year, death year, etc. You get patterns like this, and you can go count their precision and their recall. So he built the system, and he learned several million facts for 900,000 people. with the precision between 60 and 80%. Of course, you can't measure recall really because you don't know how many facts there are in the world, but you can get some quite useful information. So other colleagues of mine, Patrick Pantel and a student from Italy, from Rome, who was with us for a year, they take this and they apply this to the chemistry book and they say, how can we learn relations in chemistry? Because that's a small corpus, only one book, only 300,000 words. So they use mutual information to learn patterns, and up there's the formula for mutual information. P is the pattern, and X and Y are the left and right contexts. So it's just the obvious formula up there, right? How often do you see words, pattern, words, where you see the words but no pattern, or the pattern but no, not the same words? What's the point-wise mutual information there? And then you can remember the reliability. You see how many times you see correctly and not correctly as the ratio, etc. Given those patterns there, these little regular expression type patterns, go and throw them at the book and see what you can pull out. How many times can you find how many atoms is there in an element? What's the atomic weight of an element? Whatever. Find out which patterns are useful from the book and go learn them all. And so if you want, you can go to Google and go do the same on Google and see what do I find outside in the world, what you find in the book, what's the comparison to do a redundancy check. And then find, sometimes if you find too few, you can drop modifiers. So when you have proton is a small particle, where is one pattern, what is something else, you can drop the small and just get proton is a particle. Or expand using WordNet hyperness. Hydrogen is an element, you can get nitrogen is an element because WordNet tells you hydrogen and nitrogen are similar kinds of things. So you can learn a pattern for is-a, and a pattern for weight of, and a pattern for etc. You can go find from the book this information, you can expand these facts, and then you can get them and put them into logical form like this. If R is an S, you write it for logic like R implies S. If R is a part of S, then for all X, if it's true that R is this thing, that X is this thing R, then there is some Y such that it has the part. It is the part of this X. That's the way logic wants it. So that's just a simple transformation. There's no information loss. You just rewrite it. So these are the patterns that were learned. These are the patterns they put in. For the is-a relation, they defined gold is a precious metal. They tell the system to learn the patterns. That's what they tell it. Nitrogen is an element, and so on. The system learns the patterns and comes back saying that Na is an element, protein is a biopolymer, HCl is a strong acid, and so on. Okay, and then there's the part of relation it learned. There are also 12 seeds, the reaction relation, production relation. And it went, as I described, and learned these facts and built this little table here. The system they called Espresso, and here you can see the number of instances it learned, the precision, and the relative recall. That is compared to our 2002 paper using the old system. If you take this as how much did this system learn, then the old methods used 3.5, 3.75 times more in recall. If you look at the part of relation, then the old system learned only 58% of the new one. For the reaction relation, only 53%. Of the production relation, only 80% of the new one. But this one got much higher precision overall, and many more relations. This is a paper in Coling ACL 06, just the past few months. So you can go read up about this method there. Okay, so to summarize all this stuff, we've got this little pre-ontology, right? We've got thousands of these relations that we learned. We've got all the English sentences converted into the simple form, and a small set of relations, as many as we could in the time, through this bottleneck of producing the deeper form with all these little rules we had to write to the deep form. Now, what do we want to do? Now we come to the evaluation part. We want to, of course, enrich the English, give it more knowledge of English, and build all these more rules and so forth and so on. But at the bottom, we want to test how good is it? Is it useful yet? How do you test? Well, we take the questions. We see what kinds of questions and how many questions can the system answer. Okay. So now we come here. Now, are you asleep yet, or are you still with me? Eh? I'm sorry, this is not, I warned you, this is not the kind of talk you like to hear. You like to hear statistics and numbers and little games with numbers. This is a different kind of talk. When Dvorak sat in his little flat in Prague and said, am I going to New York or not? He didn't know what New York would look like and what his flat would look like. He had to say, oh, maybe it's this way, maybe it's this way. I don't like it, I'm comfortable here. You are now feeling uncomfortable. Maybe this is not your future, but maybe you will go to New York, right? So just listen and see, okay? See what you think. To do the evaluation, this is the way we planned to do, right? You take a set of questions from the book, not the ones involving formulas and pictures and things like this. Then you ask the system, before it reads anything, questions, and you see what it says. Then you read the sentences, but you don't do inference, and you see what it says. And then you read the sentences, and you allow the system to apply its internal rules to think and build more graphs, and you see what it says again. And hopefully, you get an increase in the number of correct answers you get out. Yes? That seems like a simple evaluation. To do this, you need a knowledge... Pardon? Oh, the first sentence, the first time, you have the system with no reading, and you ask it some questions from the high school textbook, and you see what's the correct answer. The next time you read the sentences, you just put them in the system. You do not apply the system's internal reasoning rules, and you get the questions, you get the answers. So it cannot take a graph and say, you told me this last time, now you tell me this, I can put these two together and infer something new. I'm not allowed to do that. I just get the basic facts. And then, the third time, you say, I get the fact, like all atoms have protons, and I get sodium is an atom, or something like this, or sodium, all elements have protons, sodium is an element. Now I can say sodium has protons. I allow the inference in the third step. And now when the question is, does sodium have protons? The answer will be yes. So I allow the system to do its own reasoning using the knowledge that it had before for the third level. Okay? So we see how you can do this stuff. To do this, you need a knowledge representation system called PowerLoom, or any knowledge representation system. We take the one at ISI called PowerLoom. It has been used by more than 100 places all around the world. Lots of people. It's not so hard to use. It doesn't require all the crazy logic-based consistency and completeness that most KR systems want. So here are some examples. If I say each element is composed of extremely small particles called atoms, I must point here with this, then here's how I say it. There are atoms called X, and for all atoms, if it is an element, then there exists, my cursor is gone, then there exists extremely small particles, which are called atoms there, and they are parts of these things. There's the composition, they're the compose of, and there's the set, right? So this logic I tried to show you earlier, the notation, that's what this is here. So I can ask a simple question. Is each element composed of extremely small particles called atoms? And you ask this, if I have a subject and its element, is there an extremely small particle called atom that is part of this thing? And the system comes back and says, true. Yes, why? Because it matched this to this and says, yes, I found it there. I found it in my knowledge. So I can say, is each element composed of extremely small particles? Forget that called atoms. So here's a shorter sense. Yes, I can match it. I can do subgraph matching. I still found it. I found the subgraph is true. Is each element composed of particles? Even shorter. Yes, it's true. Good. Is each element composed of atoms? Well, I didn't tell it. I said particles. It's composed of particles, and these particles are called atoms. So the system says, I don't know. Yes, I know it's composed of particles, but I don't know if particles are called atoms. I don't know the meaning of the English word called. So you have to define this sort of meaning. What does called mean? And here's the rule for called. If there is a Y, and it's defined calling Y's are Z's, the same thing as Z's, then it is also true that there is a thing called Z, then it is true of Y, it's also true of Z. That's what's the English word called? That's what it means, right? Now you can say, oh my God, who's going to build this stuff? The answer is James Postoyevsky is going to build this stuff. Why? Because he's worked on lexical semantics all his life, and these are the kinds of meanings that lexical semantics, that's what it means to mean, right? And so somebody has to sit down and figure out how these things, what they mean, and how they are reflected in English, and then somebody has to think of a clever trick, like my student, for saying, in English, this is what you get, and in logic, this is what you want, and how you learn this stuff, and that is the work for you guys, right? When one has the basic meanings of the basic words like this represented, and I believe it can be done, actually. I don't believe it's so impossible as it sounds. Then you throw this for the small set. How many were there? There were about 400 English nouns you'd have to learn and 50 English verbs to cover about 92% of the chemistry book. It's not impossible to do, right? Then you will be able to answer a question like this. Is each element composed of atoms? Well, now I have the atoms, but I use this rule of something is called something because I know it is composed of particles. They're called atoms, therefore it's also composed of atoms, and the answer is true. So you can see, step by step, A little bit of knowledge, a little bit of knowledge, a little bit of knowledge. Some from the book, some from English, some from the axioms, the meanings of basic axioms like for all. When you put them together, your inference, your knowledge grows. You get more knowledge out there. So almost finished here with this piece. Atoms are neither created nor destroyed in chemical reactions. Simple form, we just have there is a neither, there's a nor, create, destroy. Just every English word goes to everything. When we ask, are atoms created? It says true. But they're not true. Why? Because this thing doesn't understand the word of neither or nor. So you have to go and define what neither and nor mean and put them in with not. Again, it's one of these what they call closed class special logic operator words, of which there are not hundreds either, right? And when you do this now, then the system says, no, I know it's not true, false. One more example. You can use the same rule for multiple types of answers because they unify with any empty pieces, right? Bases have a bitter taste and feel slippery. So here's what the English goes to. There is a base, and there's a feeling of slippery, and there's a bitterness of taste. There's the bitter taste. There's the feeling of slippery there. You put this into the system. Now you ask, soap has what taste? And the system can go and says, here's the question form, and there's a taste there. It holds what is true of this, of soap. There we have soap in the higher part of the for all. There's soap. We've got soap, and we want to know what is true of soap. And it matches their bitterness, their EC5 and OC1, the question mark variables, things to match there. And their slipperiness, EC6, EA6 and OA6, they also match the same pattern. And therefore we get taste and bitterness coming out. So the point of this slide is with a simple rule and a simple fact, you can actually extract more information. You don't have to have one rule for one fact, right? So there's a multiplicative effect there. And the same comes here. There's more there. So, yeah, I'm running out of time. What I wanted to say on these two slides is we then went to look at all the questions in the book for chemistry and then create a type for them so that we can create the basic rules for each of these types there. Here's the question forms there. And then match them into the knowledge base to see how much was read. Now we come to the disappointment of this. Because DARPA is in a hurry, they decided to interrupt the project and to create a new project. So they stopped us in the middle of the 7th month or 8th month and said, don't do this evaluation anymore. Now start building a demonstration system, which we will go and show to DARPA on December, I think, 11th or 12th, where DARPA will bring their text to the system, and it will read, and it will answer questions, and it will show stuff. And if they like it, then they will hopefully create a new program to fund this work. And if they don't like it, then they won't. So I cannot tell you, I still cannot tell you. If you look in the book, the paper stops here and says, I will tell you at the time of the talk what's the evaluation. I'm sorry, I cannot tell you what's the evaluation. I cannot do it because they were stopped and they say, now you must do all your work on this. And so we work with Jerry and the students and everything. We work on this new part. So if you visit me in 6 months' time or so, when we're finished with the old part, we can finish this work. I apologize, I cannot tell you. I know Fred will kill me for this, but okay, too bad. What can I do, right? You are now DARPA. You must decide if you believe me. If you don't believe me, okay, vote no. So now, very quickly, this Mobius project. They say, okay, stop the work. We take 3 teams from the big group, and we just build a demonstration version which we can take to DARPA running on a laptop. So here are the teams. There's us to do the language. There's the team from Texas to do the knowledge representation and reasoning, and the framework is SRI. David Israel and Jen Baker. We take the heart. That is our domain, just the heart. And so DARPA will bring us one new paragraph we have never seen before. The system will read about the heart, and we will look what has the system learned. So we download all these. We download a whole bunch of texts, and we learn about them. We classify their different kinds of parts. We get different texts from my colleagues there. We build generic models of pumps and fluids and things in the knowledge representation part, but nothing about hearts. On the right is an example heart. We use Charniak parser and context parser. We got a whole bunch of questions. And so the system looks basically like this. First we parse, then we produce the logical forms, then we produce the triples, the third part. And so that part we do later if we do this. So here is an example. For the heart is a muscular pump, the parse tree at the bottom, the logic form there, simple form. Then this we can do well. This is bottleneck, but we're managing to do for the heart domain is small. Then we get these little triples. The heart is pump muscular. Again, you see there, ignore the red stuff, but you see there's X's and E's, the eventuality, all the same stuff as before. And we go to knowledge representation. And so now we must do a small little test. So here's my evaluation for at least this. 2 weeks ago, I took a new paragraph that the system had never seen before. Here's the paragraph in the letters. I give it to the system. I say, run. And for every set of triples that comes out of this engine now, count. How many are correct? Just do simple recall count. And so we get there. There's the recall at 2 levels. First, 4 out of 4 at the level of the logic form, the simple HNF form, and the second one, 8 out of 8 out of the triples, the sort of deeper logical form. And so the average there is about 65.9% at the logic form level and 47.8% at the triple level. That's recall. The precision, there's only one place where the precision really mattered, which was here. The verb interpretation was wrong. It did produce a lot of things, but it was completely wrong, so we killed it. So that reflects some precision in there. We didn't count the precision either. But the precision is about what it did produce is essentially right, except in this one case. You can count the precision as 100%. That's why it wasn't so interesting to do. Here are the phenomena that were problems, but we knew that from the beginning. Okay. That means that with about since August, middle of August to middle of September, about 1 month of work, redefining the system and doing this, we can get to this level for a small domain of a heart. And this is now what we will show. This is a notional idea what to show to DARPA. When you read, the heart is a pump that works together with the lungs, for instance, if that is their sentence, you get this little thing. There is some pump, which we know about. Here's the heart, which you're telling about. Here's the lungs you're telling us about. We know that the heart has some fluids. That's in the basic model there. And so we found this. The green is what we knew before. The red is what you've just told us in the text. The blue is what we inferred from what we knew before. What's there, and we just pulled it in because it seems to be possibly relevant. Pumps have fluids. So maybe we think maybe the heart will have a fluid, right? If you click on this and you say, tell me about heart, here are the little facts that come out. Not now in more English. We don't want to show the logic to DARPA. Here are the little facts that come out of what you told us. The red is what you told us. The green is what we knew. And the blue is what was inferred from what we knew. And if you click on a pumping device, here's the model of what we learned about the pumping devices. Okay? Now, here is the end of the story. What's different from the 1970s? Yes, we can do large-scale parsing to sort of 50, maybe 60% correct. When we go to the logical form, that's a bottleneck. But I think with training data, we can actually learn to do that. You can see it's a small set of small steps, which you are used to doing because that is what this community does. To get to the deeper, the triples, that's not so hard because it's a small set of phenomena, negation, quantification, etc., etc. For those, you need the expertise of logicians and semanticists and people like James and so on, and those people exist. And they have been working on this. If you just have them work together within a hard constraint of time, you will get for the phenomena that your textbook needs the right things, that you can actually do some inference. Not all, but some. The semantic phenomena, like these things, well, people have thought about this. I think you will be able to get some reasonable level, not deep answering, but simple question answering out. Inference is there, knowledge representation technology is there, and it's more robust than it was in the 70s. It's still not used to having lots and lots. It has never scaled up yet, but that's their challenge. Evaluation, it's not clear how one can do this properly. So here is my score on each of these things. Maybe I'm optimistic, maybe not. You can judge. Soon we will vote. So should we try? Some people say, yeah, we must try. This is a future that takes us out of this little game of just throwing text in and doing numbers and combinations and things. It takes us to a new level where we actually bring a whole new technology in, namely reasoning, and we have a new future out there which is richer than just information extraction, information retrieval, text summarization, machine translation, speech recognition. And other people say, no, we are still too far off. Knowledge representation is too brittle. It's not robust enough and big enough yet. And language is too crude. It's not able to go down to the deeper levels that we need yet. Okay? And so now I ask you, should we try learning by reading or should we not try learning by reading? If you are DARPA, ladies and gentlemen, what is your vote? Who says no? Nobody says no. It's not your money, I can see. Who says yes? A lot of people say yes. You stun me. I'm completely surprised. I thought most of you would say no, because it's very different from your paradigm, and it is in the field where you are suspicious, where you say this is crazy and weak and so on, and that is true. However, it is New York. It is interesting. Maybe there is a new life there. Yes? You can still come back to Prague if you want to. Yes? So this is the essential question that DARPA is asking, and by December 12 or 13, I don't know how long, but Tony said that it doesn't take long to make up his mind, we will know. Is there a future here for us in this kind of realm where we can bring knowledge representation and language together again after 40 years, or is there not? Not yet. Thank you very much. Louise.
I just have a little question. It was a nice talk and it's a great idea. But the engine for reasoning looks very prologue-like. Is it? I know it's not your part, but is it more than the resolution implemented in prologue? Does it give us more, or is it just? Are they just using prologue?
That's a good question. It's more than prologue. It is at heart like prologue. So it's a backward chaining, abductive inference. But this engine can do forward chaining too. That's one thing. It has all kinds of controls set in, so it doesn't have to go to the deepest, fullest logical extent.
The criticism of prologue is normally the negation as failure kind of thing. Is it trying to overcome that?
Yes, it can. Yes, yeah. It has a technique. It's not my specialty, right? But there is a technique called why not, in which they work with constrained sets in which the negation by failure, the failure by negation, can be controlled, can work. But you make your assumptions there, right? You have to close. You have to work in limited worlds. So they do. These guys, PowerLoom and one or two other places, have addressed very seriously the concerns that came from Prolog and the heavy-duty knowledge representation people from Toronto and elsewhere, where they say it must be fully complete, it must be fully consistent, and so on. Otherwise, it's garbage. The world is not that way, and so they have worked very hard on making certain limitations to make it tractable, yet not so small that it's a joke. That's the trade-off in KR. James? Yeah.
I'm sorry, just one comment relating to that question. I think with the systems you're talking about, you're assuming reasoning over a finite domain, so it makes it a very different issue if you want to deal with negation. So it is tractable.
Yeah. Yeah. So you have a question.
For me, this task of learning by reading is very similar to question answering, and some of your examples are also very similar to the task of textual entailment, in particular those of answer validation.
Yes.
It's not the same thing with another name?
That's also a very good question. I'm glad you brought it up. It is the case that the textual entailment community, which started 2-3 years ago with Ido Dagan and others, is moving into inference. They don't call it inference, they call it entailment. They don't think of logic or anything, they think of text level. And they go through large amounts of corpus where they just see, when I see this word on the left side, can I see this word on the right side? And if you give me right side words, can I then say it entails left side words or right side words? That's the game they play. And they have these competitions, right, the normal type competitions, and they get, 50%? Something like this, okay? So it's not the case that this is just pure logic craziness. It is the case that a certain community, a certain group of the machine learning, language processing community is already moving here. They are obviously people who would be interested in this, and if they had a corpus of not just text to text, but text to deeper form, sort of simpler form, and they could learn that, and from that they could get better entailments, better than 50%, they would use it tomorrow. Some of them would use it tomorrow to win the competition. I believe this is going to happen. All right? So that's one piece of evidence that this is now ready, and people are feeling their way towards something deeper. They don't know what the deeper is yet. This logic form may not be the right one. I don't know. It's just the one we chose. Question answering is then the next step beyond entailment. And the best QA system, the LCC system, has been using this kind of logic entailment with this kind of Hobbes logic for already 4 or 5 years. That's why they win. They get 10% better than anyone else. Sanda Harabaju, the designer, and Dan Moldovan, Sanda studied, she went and did 1 year postdoc at SRI with Hobbes, who designed this notation. That's why she uses that notation. So there's another piece of evidence that maybe this is a useful thing to do in the sort of statistical paradigm measured against purely pattern-based, simple, quote-unquote, statistical question-answering engines. So there's another piece of going there. Yes?
Yes, I just wanted to take you back to your slide that said you need knowledge of English and push you a little bit on this. Because turning on a chemistry textbook alone raises the question, how robust is your question answering system going to be? So the questions that a user will pose, I think you gave the example each atom is composed of particles, and you gave the answer that the system could answer the question, some question like, is each atom composed of particles? And supposing we say, does each atom contain particles? Supposing we say, are there particles in each atom? Supposing we say, what is an atom made up of? What do particles combine to form? You could sort of go on listing them forever. Where does it break down? How robust is it?
Good question. This is the whole tension, which I mentioned just briefly, between the ontological promiscuity and the small primitives. On the scale of, are you going to take many different words and have each symbol mean something ostensibly different because the system doesn't know that all these variants mean the same? Or are you going to have just one representation symbol for all this composed of? And is somebody going to give you the semantic mapping of all these words into this one thing? Who knows, right? I can imagine two different approaches. One trying the primitive approach, which is where I grew up as my advisor. One trying the promiscuous approach with lots of symbols, and then some machine learning ways to find synonymy or semi-synonymy between them. And I think, in my heart, I believe the second one will work better. But as you say, it's a whole different enterprise to learn semi-synonymy between different phrasings. But that's, again, not something that is completely unknown to this community. People, like my colleague Patrick Pantel, are already doing this. They're talking about clustering words together with the same sets of meanings, finding relationships and saying these words are all the different phrasings of the same basic relation. So I think that's going to come. I don't think it will be perfect, and I don't think it will be complete, but I think it will be there enough to allow the sort of recognition of quasi-synonymy. In fact, just the final comment, I know I have to stop. One of my students just gave a paper at Coling on using quasi-synonymy or paraphrase to enhance machine translation or summarization evaluation. And what she did was a very simple trick. She looked at the English-Chinese translation tables, and she said, here is the English, and here are all the different Chinese ways of saying this English. Or vice versa. Here is Chinese, and here's all the different ways of saying this Chinese thing by translation learned from corpus, right? And with each one there's a strength. So she says, assuming that they're all roughly correct, when I pick out a single Chinese thing, here are the paraphrases in English that mean the same thing. And so she puts them in tables, and she learned about 130,000 tables of equivalence. And they look quite reasonable. They don't look crazy. So one can learn this. There's the answer. Thank you.
I can't allow you a question because I've been told we should close the session. But I'd like to make a comment that you wrong us when you think that we are not interested in meaning. Of course, everybody is interested in meaning, and everybody knows that text and analysis, etc., has to do with meaning. The problem is that this meaning notation is so tedious, and it's just very tedious, and it's very hard to evaluate, and it's still on the human to say yes, with all these parentheses, these things correspond, and so far and so forth, as opposed to straightforward things like machine translation, or as opposed to straightforward things like speech recognition, or even parsing, where the notation is something that a human can understand and can debate.
So there, I knew Fred wants to have the last word, so I'm going to have the last word. I don't agree. I think parsing is more difficult to read than these things, and more difficult to evaluate, because these things you can do in question answering. And if I had a convincing question answering story, where you type English questions, you get English answers, you never see the logic, and the answers were correct, you would not be able to make that claim.
Okay.